Good afternoon, ladies and gentlemen, colleagues, and students. Welcome to this afternoon's Technology Forum, Advanced Materials for Better Quality of Life. So all of you know, this year marks the 30th anniversary of CityU. So over a very short period of time, CityU has grown tremendously, and research activities have played a very important role in the rapid growth of CityU. And research now is well integrated into the quality education that CityU provides in the form of our signature discovery-enriched curriculum. It's really my pleasure to chair this forum on advanced materials for better quality of life. So today's event kicks off a week-long celebration of 30 years of research and innovation at CityU. Some ask me how I picked the title, Advanced Materials for Better Quality of Life. So to answer this question, let me just quote from Alexis Carrel, who is a Nobel laureate in medicine and a pioneer in transplant surgery. So he said the quality of life is more important than life itself. So that was interesting to me. As you will find out today, that the range of materials or topics covered in this session is very, very broad. But they all underscore a common theme, and that is, at the end of the day, whatever we do, materials discovery, innovation, and technology development, whether they're in energy applications, bioelectronics, they're all intended to improve the quality of our life in the society. So today I'm very pleased to announce that we have 5 distinguished speakers with us today. They are Professor Mark Astor from UC Berkeley, Professor Despina Luca from University of Virginia, and Dr. Peggy Lowe from the Department of Biology and Chemistry at the CityU, Professor Andrei Rogach, Chair Professor in the Department of Physics and Material Science, and Dr. Roy Valasamy, Associate Professor in the Department of Physics and Material Science. So the format of today's session is as follows. Each speaker will give approximately 30 minutes of presentation, and at the end of their presentation, I will call all of them come on stage. So sit here, we'll have a panel discussion. That will last about 15 minutes. That's where you're all invited to ask questions. Let me proceed with the first presentation by Professor Mark Astor. The title of his talk is Materials Discovery and Design, the enabling role of computational modeling. Professor Astor is the department chair at Department of Material Science and Engineering at the University of California, Berkeley. He received his PhD from UC Berkeley, and then he has worked at a number of places at Sandia National Laboratory. He also served on the faculty at Northwestern University, UC Davis, before returning to his alma mater at UC Berkeley. In 2012, he was appointed Department Chair of Material Science and Engineering Department at Berkeley. His research area focused on the development and application of atomistic and first principle methods for computational simulation of thermodynamic as well as kinetic properties of multi-phase materials. Professor Astor was awarded ASM International's Materials Research Silver Medal Award, which recognizes a mid-career material scientist whose individual and collaborative work has had a major impact on the science of materials. In 2010, he was elected a Fellow of the American Physical Society. And in 2012, he received a Distinguished Scientist Engineer Award from the Electronic, Magnetic, and Photonic Materials Division of TMS. Let's welcome Professor Mark Asta.
So advance like this. Yep, okay, great. Okay, good afternoon. And I want to start by thanking Shunli for the opportunity to be here today. It was a long flight from San Francisco to get here, but I've really been enjoying the time here, and I hope I can deliver a nice talk for you guys today, despite the jet lag. So, okay, so as you heard, I'm going to be speaking about computational modeling. That was the invitation I had, was to speak on this area, computational materials science. But to kind of fit into the theme, what I want to talk about is really using modern computational tools to aid materials discovery and design. And this is work that's done in very close collaboration with a number of people, not only on the Berkeley campus, but also at the Lawrence Berkeley National Lab in Berkeley. Okay, so let me start by sort of giving a very broad overview about the general idea that materials play a very important role in advancing quality of life and in addressing major issues that we're confronting as a society. So, you know, whether it's modern day flat panel displays or advanced materials that have enabled more fuel efficient aircraft, advanced polymers that allow us to do things like holographic images for security purposes, transplants, or this is actually a knee here that you're looking at, so a biomedical application, new materials for advanced infrastructure, information technology, and of course fiber optics, or in the area of sustainable energy. There's a lot of very interesting developments that are a direct consequence of new materials. So basically the story that we always tell our students in materials science and engineering is that the advancement and design and optimization of new materials really is cross-cutting and enabling technology developments across a broad range of engineering applications. But let's think a little bit about this process by which we discover or which we choose a material for a given application. Okay, so this is a little example that's taken from a very recent Scientific American article by Garrett Sater and Christine Pearson. And they reviewed basically the process by which Thomas Edison first came upon the selection of the material to use for a filament of a light bulb. Okay, so as this says, what Edison did was very much what we nowadays call Edisonian style research. He tried many different kinds of materials, and he did this by focusing on carbon-containing materials to try to find a good filament for his light bulb. And he searched over 3,000 different materials and finally ended up with a filamentous material that he thought was the best choice. Well, in fact, it wasn't the best choice. The tungsten filament was invented many years later, and it basically persisted to all this time. So I wanted to give this example because it really characterizes what we call Edisonian style, that when we're looking for a material for a particular application, the sort of traditional approach in our field has been to trial and error. Okay, trying many different kinds of materials and seeing what works best for a particular application. Okay, and this has served us well, of course, throughout time. We've had a lot of innovations in technology due to the development of new materials. But it's kind of interesting to take a look at this data which was put together by Tom Eager back in '95. And what he was trying to point out here is thinking about some materials that have been very important in different technologies, okay? For example, permanent magnets, energy storage materials, aerospace, and so forth. And he put together a little timeline where what these bars are supposed to indicate is sort of the time when a certain material was discovered, sort of at the laboratory scale for a particular application, and then all the years that it took until it saw commercialization. Okay, so an example here is the lithium-ion battery that we're all very familiar with. You know, we wouldn't be able to carry around our iPhones and iPads and so forth if it wasn't for lithium-ion batteries. But basically, the discovery of the cathode material which enabled these is in the 70s, and you see it wasn't really until the 90s that we had that commercialization. So the statistic, sort of the number that came out of this analysis was that a very typical time frame for development of new materials is, well, he quoted 18 years, but 10 to 20 years. And of course, a lot of trial and error experimentation, a lot of time, a lot of human effort, and a lot of money in R&D in making this happen over that time frame. Okay, so clearly development of new materials is in some sense then a bottleneck for how rapidly we can innovate in new technologies. And these technologies, of course, are cross-cutting many different themes that occur in sort of advancing a better quality of life. Okay, so this in the United States was basically the impetus for this idea of a materials genome initiative. And this was something that was announced at Carnegie Mellon University in June of 2011 by President Obama. And it was part of a speech where he was talking about the National Manufacturing Initiative and basically the idea of really trying to revitalize manufacturing in the US. And what he was hitting on here is the idea that we can basically try to do better in the innovation, the time frame for innovation of new materials. Okay, so basically the last line here is we can do it faster. So the concept came together that we've had big advances in computational modeling and experimental tools and in how we basically handle data. And by bringing those all together, the goal of this initiative is basically to make materials development twice as fast at half the cost. That's sort of the slogan. But I think more important, the way to think about this is very much the way that a company like Apple Computers does nowadays, that basically what you want to be able to do is when you're designing a new product, you want to be developing the material in parallel with the product design. Okay, so that process should basically take the same amount of time as developing the product. So you're not limited by the materials you have, you're developing the materials you need in this process. Okay, so that's basically the idea, and can we get there? Well, there's been a certain amount of money that's been devoted to pursuing this general idea in the US, and what I wanted to give you today was a little bit of a kind of a snapshot of some of the things that have progressed in the area of computational modeling within this broad umbrella. Okay? All right, so what is it that kind of limits us in our ability to discover new materials for a particular application? Well, one of the things that's pretty striking is to think about the fact, if you're thinking about making a material out of an inorganic compound, okay, so a hard material, if you go to the International Crystal Structure Database and you basically count all the compounds which have ever been synthesized and characterized, depending on exactly how you do this, you end up somewhere between 50,000 and 200,000. Okay, then you go to your favorite handbooks and you start to look for, of all those compounds, what do we know about them? Okay, well, they've been characterized or they wouldn't be in the ICSD, so we know their atomic positions, but how much more do we know about them? Okay, so if you simply ask a question, for example, for how many materials do we know the elastic constant tensor? You get about 200 compounds if you look through all of that, all the handbooks. How many do we know the superconducting transition temperature for? Actually, surprisingly, a lot more than elastic properties. Dielectric constants, okay, a very fundamental property, around 300 to 400. Okay, so what this statistics is trying to tell you is that we really don't know very much about all the materials which we've made in mankind so far. Okay, about below 1% coverage for some of these physical properties. Okay, so that's really a hindrance then if we're trying to explore and look for new materials for a particular application. For example, if we're looking for the best battery cathode, the amount of material we know about most of the inorganic compounds which might be candidates is very limited. Okay, so here's the basic idea is that if we want to know much more about materials and be able to discover new materials, let's think about the role of computational materials science. Okay, and that's what I'm going to focus on in the rest of the talk. And what I want to do first is to introduce you to the basic idea of first principles computational materials science. And the best way to do that is to start with Dirac. Okay, what do we mean when we say that we're doing a first principles calculation? Well, this is a quote from Dirac in 1929, where he was commenting about the fact that the theory, quantum mechanical theory, for many electron systems had been developed theoretically. And so he's basically saying we now have the mathematical treatment for all of physics and or part of physics and the whole of chemistry. So basically we have the theory to basically explain chemistry and how atoms interact. The difficulty lies only in the fact that these equations are too complex to solve. Okay. So fast forward then to 1998, and now here is a quote from the 1998 Nobel Prize in Chemistry. What happened from 1929 through the years to 1998 is that we found ways of basically solving these equations in a way that's very computationally efficient. So we're basically at a point now where we can solve these quantum mechanical problems and predict computationally the properties of a material or of a chemical compound. Okay, and that's what the 1998 Nobel Prize was recognizing, and they remark here the consequences of their work, Walter Kohn and John Popel, was revolutionizing the whole of chemistry, and these techniques are also have carried over and had a big impact on the development of materials as well. Okay, so that's basically what we mean by first principles computational materials science, is we're using the quantum mechanical theory to explain how electrons interact in a solid, and from that, making computational predictions. Okay, so we're at a point in time right now where, we have very powerful supercomputers, and we have pretty good quantum mechanical theories. Quantum mechanical theory itself is perfect, but we have pretty good computational implementations of it. We can combine that with basic laws of physics, crunch it on a computer, and predict a physical property of a material, starting really only from knowledge of the atomic numbers of the elements and where the atoms sit in the crystal lattice. Okay? What's particularly powerful about this is the fact that these calculations are relatively fast and they're scalable. Okay? So basically, the more nodes you have, the more you can do. Okay, so I'm going to give you some sense of how much information now we've been able to develop in just a short amount, about a year of working in this sort of mode. Okay, so we've gotten to a point now where instead of computational materials science sort of considering one particular property of a material for one particular compound and trying to understand that in detail, we've gotten into a mode of something called high throughput computation. And this is very nicely reviewed in this review article in Nature Materials from last year. Okay, I'm showing two examples from that article, one from Alex Zunger's group on the left and one from Jens Norskopf's group on the right. And the first thing that you see here is that there's a lot of data, okay, and these are data that probably took a few months to calculate. And what they're doing is they're considering two particular applications. On the left, photovoltaics, so they're looking at materials which will be very good absorbers of light in the solar spectrum, okay? And so they're plotting here the band gap of the material. And on this axis, over here, there is a so-called discriminator that has been developed to tell you how well this thing will perform in a solar photovoltaic application. And so what they were able to do is screen through many, many inorganic compounds with similar crystal structures and basically found the known best performers and several new compounds that people hadn't yet considered. Okay, a similar example over here in catalysis. Here, what they're looking at is the hydrogen evolution reaction, a catalyst for that, and they're looking at binary alloy catalysts. And they're plotting now two different discriminators. Okay, so I'm using this term discriminator, which basically means a property which helps you predict the performance. And one is the binding energy of hydrogen on the surface, and the other one is a stabilization free energy. That's how thermodynamically stable this material is. They find that basically what you want is materials over here in this corner. Okay, the lower the hydrogen binding enthalpy, the higher the activity. And what they find is that here's platinum, which is a well-known good catalyst, but they actually predict a higher performer in bismuth platinum, okay, by doing this purely computationally on the computer. And they actually went ahead and made that and did find that it had a higher activity than platinum. Okay, so these are examples where we're using computation in a mode where we're screening over many, many different chemistries and trying to find the best material. Okay, so these are two examples from the literature. Now, the idea has come about that why do we just do this on a case-by-case basis when we need to consider a particular property? What about just going through all the known inorganic compounds and calculating every property we can from quantum mechanics and storing it somewhere where people can access it publicly? Okay? Believe it or not, we're not too far away from doing that. Okay? So this is showing you then the same supercomputer that I showed you earlier. By the way, this is the supercomputer at the National Energy Research Supercomputing Center, Scientific Computing Center, NERSC, which is at Lawrence Berkeley Lab. And what we've developed, or what the group at Lawrence Berkeley Lab, led by Christine Pearson, has developed, is basically a lot of computer science tools which drive our quantum mechanical codes and calculate any property that you want, using only as input the atomic positions from the International Crystal Structure Database. So there's really a very sophisticated workflow that goes on here, but at the end of the day, we end up populating a database where for a given known compound, every property that we can calculate from quantum mechanics. And then the idea is to make this accessible to the public and let whoever has a particularly interesting materials design question be able to access this. Okay, so here's a website that allows you to access this information, and those of you who are already bored by the talk can pull this up on your cell phone and see this really exists. So this is a web-based portal, basically, to this big database that I talked about earlier. And what you see here is a periodic table and a bunch of different apps that work on this computed data. So let me give you an example. Okay, so what does this have? Well, right now, for about 55,000 compounds, this database has the energies of the materials, certain things related to thermodynamic stability, certain properties related to performance in batteries, because DOE funded this initially for battery work, 25,000 band structures, and as I said, phase diagrams and things related to stability in aqueous environments, Porbet diagrams. And we're still going. Basically, the goal is to get all the way through the ICSD database. Okay? So here's something you can do. So basically, the idea is we now have something like a Google interface for materials discovery. So here's an example. I take the periodic table and I say I'm going to pick iron, which is a nice earth-abundant, cheap material. And I say I want to know all compounds that include iron, which have a band gap between 1.5 and 3 electron volts, contain no rare earth elements, and are either thermodynamically stable or metastable, very close in energy to the thermodynamic state. So I put here iron, I put the number of elements that I want to consider, 2, I exclude all the rare earths, and I dial in the band gap and something about the thermodynamic stability. I hit go, and it tells me there are 6 materials in the ICSD database, or in the database that they have currently, that have these properties. And I chose this basically because I knew hematite would pop up. This is sort of some properties you would want for a good photocatalyst. But what was surprising is that in addition to hematite, there's this iron fluoride compound that was sort of a surprise that one also has some interesting characteristics for this application. Okay, so that's the general idea, that the computation now is not going to just be running a code, but actually populating databases which are publicly available and can be used for materials design free of charge, completely open source. Okay. All right, so we're kind of in an era where this sort of high throughput computation and materials discovery is going on in a lot of different contexts. I list a lot of properties that I know groups in the US are working on where they're computationally screening for new materials, both in terms of optoelectronic properties, in terms of electrochemical properties, and so forth. One thing that's not really been looked at too much is mechanical properties. Okay, so I'm just going to spend a couple minutes. How much time do I have? About 5 minutes or? 10 minutes, okay, great. Okay, so one of the things that I got involved in the materials project was to try to bring some properties related to mechanical behavior into this, because in addition to all these functional properties, we'd also like to know that our material can sort of withstand a certain amount of stress and strain in a practical application. Okay, so first of all, I didn't know what the audience today would be in sort of the background. So what do I mean when I talk about a mechanical property of a material? So let me go back to really the introduction to material science kind of level. So imagine I have a material and I pull on it, or I put a weight on it, and it's a so-called tensile test in two directions. So I put a stress, a certain force per unit area. As I increase that stress, the material is going to elongate. That's the strain that you see here. Okay, and this is a classic sort of stress-strain kind of curve for a metallic material. Now, there are certain features on this curve which are interesting in terms of engineering a material for mechanical performance. One is the initial slope. Okay, this is the linear slope here, where stress is linearly related to strain. We call that the elastic regime. If we load it and then unload it within this regime, we go back to the original material. Okay, so the relationship between the applied stress and the amount of strain is the elastic constant tensor that I mentioned earlier, the CIJKL. Okay, there are other features like we go beyond a certain stress level, and then when we release the load, we don't recover back to 0% strain. We start to have plastic deformation. And we call that the strength of the material or its hardness. Okay, and then we can also ask how much stress can we put, or how much strain basically before the material breaks. That's a measure of the ductility of the specimen. That's basically how much we can pull it before it breaks. The more we can pull before it breaks, the more ductile the material is. So these are all features that if we're thinking about a property for a particular application, we would worry about in terms of the mechanical performance. Okay, so the whole key with this computational screening for materials is to have what we call descriptors. That is a certain property that we can calculate in a high throughput mode that correlates with a more complicated property that we're interested in for an engineering application. Okay, so a complex property is this ductility or hardness of a material. That's a very hard thing to calculate directly on the computer. But what people have found through years of research is that there are certain discriminators or predictors based solely on the elastic constants of the material. So instead of that fourth rank tensor, what I'm showing here is simply just bulk modulus and shear modulus. So already in 1954, Pew was telling us that this ratio of bulk modulus to shear modulus tells us something about ductility. Okay, and this is a review from ManU. Basically, the higher this K over G ratio, the better in terms of ductility. Okay, and so basically what that's saying is if you have a low shear modulus, it's easy to plastically deform the material. If you have a low bulk modulus, it's easy to break the material, to pull apart the bonds. Similarly, there's been a lot of work in the community looking for extra ultra-hard materials, and there a correlator or a predictor or descriptor is this ratio K squared G, which is just the shear modulus divided by this ductility parameter K over G squared. Okay, and this is some correlation between that parameter and experimental data. So for example, suppose that we wanted to use these kinds of things to search for materials which have a good balance of hardness and ductility. Okay, we have some discriminators here, but remember I told you that the amount of materials that we know the elastic properties for is very, very limited. Okay, so if we want to screen over a very wide composition range, you have to resort to actually doing the measurements or doing the calculations. Is this something we can put into a publicly available database? Well, over about the last 2 months, we've been able to finish calculations once the codes were written to calculate elastic constant tensors in a fully automated way on the supercomputer. And we're now up to 1,300 elastic constant tensors. Remember, the amount that you can get right now from the literature is about 200 to 300. Okay, so we've gone way beyond that. And this is all going to be available very soon in this materials project. So you'll be able to screen, for example, for material stiffness now in discovering new materials. Okay, so what's plotted here is the calculated shear modulus and the calculated bulk modulus on these two different axes. And these are this ratio K over G, again, is a ductility. So K over G1 would be low ductility, K over G of 5 would be very high ductility. And all these materials that we've looked at so far lie somewhere in between, with a few exceptions. Okay, these are also colored by Poisson ratio. So as you go towards more ductile, you're seeing that the Poisson ratio is getting bigger. Okay, over here. Okay, so basically we now have 1,300 materials that we know the elastic tensors for, and within the period of about 6 more months or a year, this number, will probably double or triple, probably triple or quadruple actually, okay? Now one of the things that's interesting is to look already at this database and say, is there anything harder than diamond based on the predictions on the predictor that I showed you earlier? So remember that the hardness in that predictor was a ratio of this G, okay, divided by K over G. So low K over G and high G means high hardness. Well, here's diamond right here, and unfortunately, it really stands off. There's nothing close to it yet in this database, okay? So as we go through all the ICSD, we'll see, but I'm not optimistic that we'll find anything harder than diamond, although we're on the lookout for it. Okay, so this is basically some examples then, again, of these publicly available databases, and pretty soon, if you keep track of this materials project, there's going to be a lot more properties, including thermal conductivities, elastic moduli, a whole bunch of other properties that are going to be available, hopefully with the ultimate goal of being able to make predictions for everything in the ICSD, okay? So it's a pretty huge undertaking, and the computers are generating a lot of heat in Berkeley, but we're slowly populating this database. Okay. So I want to leave you with one last example that's a little bit different in terms of materials discovery and materials design. Really what I've been talking about so far is what I would call materials discovery. We're trying to find a new material with a given property. There are other times when we do materials design where we're trying to do something like find a replacement for a given material. Okay. So I'm going to give you one last example that's kind of fun. I don't know if it's bettering human society, but it's dealing with the property of elemental rhenium. So this is a very fascinating material. It was the last stable element discovered back in 1925. It sits here right in the middle of the transition metals series below manganese. It's hexagonal closed packed crystal structure. And what's interesting about it is it has a very, very high melting point. Okay, its melting point is exceeded only by carbon and tungsten. Okay. Now, what's also interesting about this material is that it's very ductile. Okay. So it has very high strength at high temperature, but you can also form it. And if you're thinking about an application like a rocket nozzle here, it's particularly attractive because as the thing cools and heats and you have very big stresses, this material doesn't fracture and crack like other refractory metals. Okay, but here's the problem. Rhenium is extremely expensive and the worldwide reserves of it are very low. So if we really wanted to think about, using it in more high temperature applications, we basically don't have enough of it around in the world. So can we try to understand computationally how rhenium works, and then using that understanding, try to come up with a new material? Okay, so here is the basic idea for when you're doing a replacement strategy or a replacement kind of problem. So we have rhenium. We want to basically maintain its properties or build on them, but we want to lower the cost. Okay, so we make here a plot of the dollar per atom, basically, of different elements in the periodic table versus the number of valence electrons. Okay, and rhenium is sitting right here. Okay, now if we're going to try to replace rhenium with something cheaper, what we would think about is combination of metals to the right and to the left, okay, such that this tie line here in this phase diagram kind of language has a lower average cost than pure rhenium. Okay, why do I want this to have the same number of valence electrons? Well, we know that the valence electrons correlate very well with melting temperature, which is what's important, and shear modulus, which is important for strength. Okay, so we want to be there. But now what about ductility? Now the risk is that if we start making alloys that are cheaper, they're going to end up being very, very brittle. Okay, so this is using high throughput computation in kind of a different way. It's more thinking about things on a more of a mesoscale. So one of the things we know about rhenium is that if you deform it at low temperature, it has a lot of these twin boundaries which form. So these different colors in this micrograph, electron backscatter diffraction, are twin boundaries. And this material twins extremely easily. So what we ended up doing was a set of high throughput calculations where we calculated the twin boundary energy for all the HCP transition metals, many, many different possible twins. I'm only showing results for a couple here. And I'm plotting those results versus the shear modulus here. And what you see is that for these two different kinds of twin boundaries, for most of the HCP transition metals, there's a nice correlation. But rhenium is sitting way down here. It has an extremely low twin boundary energy. So what happened here was we used high throughput computation and tried to understand a certain experimental observable, namely the Hyde twin formation. We found indeed that rhenium is very easily to twin. But then the beauty of computation is you can start to go in and rip apart the calculations and try to understand why it so easily twins. And what we find is that in the twin boundary of rhenium, the atoms are surrounded by an environment which looks pretty much like an icosahedron. Okay, they don't at all look like the polyhedra that we have in the HCP crystal structure. Now, it turns out these polyhedra, these icosahedra, form in these other crystal structures, which are the so-called Frank-Caspar phases, which are shown over here. Now, we understand from the calculation something very interesting. If you take these Frank-Caspar phases, which are the A15, the sigma, and the chi, and you look at their energy relative to HCP, so HCP is this line, and these are the transition metal series. What you find is that these icosahedral type structures end up having energy that's very, very close to HCP, and it gets even closer as we go over here between rhenium and tungsten. So what this tells us is basically, and again, this came out of doing the high throughput calculations, if we can design an alloy now with an average d electron count, say somewhere in here, we're going to have this very easy twinning deformation possible. And so we think we can also control the ductility of the material. Okay. So again, this is a different kind of example rather than just of screening through a bunch of properties. It's looking at basically more of a mesoscale type of phenomena related to twin deformation. So we have now actually a new way of approaching this design of rhenium alloys using the simple discriminator of the number of d electrons. Okay, and we think this is basically the sweet spot right in here. Okay, and we're in the process right now of making up these alloys, which is not easy. You have to go through a powder processing route, and that's work in progress. So you'll have to stay tuned to see how it all pans out. Okay, so I'm going to go ahead and end. So I wanted to leave you with kind of 3 points from the talk. That first of all, in thinking about materials, the role of materials in bettering society and so forth, material science is really a field where we can have huge impact on technology and on bettering life, the quality of life. And so basically, you know, where we're at in a lot of technologies is a need for new materials or better materials to enable further advances. We're in an exciting time in terms of that because there's been rapid advances in computational tools, but also in experimental synthesis and characterization. So I think it's fair to say we're kind of in this very exciting era of materials engineering, really maybe getting close to the point where we can sort of dial in on the computer a certain set of properties and you know, have a prediction about what might be best, okay, and ways to rapidly test it experimentally. Okay, so I'm going to end there and just congratulate the City University of Hong Kong and thank you for the opportunity to take part in this celebration. Thank you. Okay.
Okay, thank you for the introduction and thanks for the invitation today from Professor Wang. Today is my honor to be here and to share with you part of my research that I carry out in Canada and in CityU today, and mainly focus on the development of multifunctional nucleic acid-based nanomaterials for biomedical applications. So all of you should know that in nature, DNA is a hereditary material in human and all other living organisms. And most of the DNA basically are localized in the nucleus, and they are the carrier of genetic information in a living system, so that's why we look different from each other. But in the field of the nanotechnology, basically we treat the DNA as a synthetic polymers and a building block to construct well-defined nanostructures for different purposes. Because the DNA, it is possibly the most predictable and programmable cell assembling materials due to their intrinsic properties. For example, in here we show that there's a cooperative balance of the hydrogen bonding between the AT and CG pairs, the nuclear bases. And also with the pi-pi stacking, between the nucleobases along the chain, and as well as with other non-covalent bonding, such that a single-stranded DNA can find a complement in the solution with a high selectivity. So we believe that the DNA would be a wonderful building block for the nanomaterial science. And in the DNA nanotechnology, basically, there are several elegant approaches that have been developed to construct the nanostructures. So the first pioneer work by Simon in 2003, he reported that just taking these holiday junctions, this unit, to convert the one-dimensional DNA strand into the branched DNA tile, and with the sticky end at the edges. And this sticky end can further assemble into 2D structures, the templates, or even highly ordered 2D assembly, with a programmable arrangement of different substances, for example, the gold nanoparticle, protein, or even enzyme. And the second approach in this area we call is the DNA origami approach. Basically, it's just taking a long, single viral DNA strand, and this strand itself fall into desired pattern by adding different short stable DNA strands shown here with the color. So once we have this kind of structure, basically you can see from these two approaches, DNA is only the molecule used for the assembly, and at the end give you the very rigid and large DNA structure. So in parallel, at the same time, another approach we call supermolecular DNA cell assembly approach is developed as well. Basically, this approach is to involve the use of the synthetic molecule in between the two DNA strands and to create the discrete multifunctional structures. Because of the intrinsic properties of these synthetic molecules, such as the organic or inorganic molecule, they will have their photophysical, redox, magnetic, or catalytic properties. So this will allow for the rational design of the final assembly with different or complex functions. And we found that using this approach, the number of the DNA need for the structural definition is also reducing as compared to two previous methods. So basically, my group, based on this DNA cell assembly approach to develop our structure. And today I would like to share with you two examples. The first one is the DNA nanotube, and the second one is the DNA cages for different function and purposes. So to do this, first of all, we have to grow or synthesize the DNA strand on a solid support using the DNA synthesizer. And here we would like to incorporate this organic molecule between the DNA strands. And after that, we cleave them from the solid support, and we close these both open ends using a template, carry out the chemical ligations. So once we have this DNA single-stranded cyclic triangle, what we have to do is try to add and design 3 complementary DNA strands here, one by one, to form this rung. And finally, we rigidify this using a short DNA strand here. So at the end, you can see this triangular rung with 3 arms, they are pointing up, and the other 3 arms, they are pointing down. And to generate a well-defined or controllable nanotube, basically we're using a hierarchical approach to do this. So in here, you can see that one side of the strands with the sticky end is 7 bases long, and the other 2 sides, they have a shorter bases, 5 bases. So what happened is that to form a tubular, one-dimensional nanotube, we add the double-stranded linking strand here, heat up the sample and cool down. So basically, the double-stranded linking strand will cohere to the longer side first to form this linear assembly before the cohesion of the other 2 sides. And we found that using this approach, we can have high percentage yield of the long tubular structure, and we also can prevent the cross-linking. And here is just the characterization using the AFM and then the confocal. And you see they are very long tubular structure, and most of them, they are in the same height and size. So using this approach, besides the square-shaped nanotube, we can also generate, besides this triangular-shaped nanotube, we can also generate the square-shaped nanotube from this square template to form the fully double-stranded square DNA nanotube. But what would be the interesting thing here using this approach is that we can also generate less rigid and more flexible nanotube by only adding one double-stranded linking strand here, and the other three sizes are the single-stranded nanotube, a single-stranded DNA. So basically, you can see the big difference between their flexibility. So besides we can control the shape and then the dimension of the nanotube, we also would like to control the length of this kind of assembly. And here we would like to use a guiding strand approach. First of all, to taking a repeating DNA sequence unit. And we only by changing the sticky end sequence number 2 and 4' here, we can add one by one to form a well-defined template with the desired length. And after that, we just put the preformed triangular round and closed tube. And based on the length statistical analysis, we found that we can really control or narrow down the length distribution depends on which template we are using the 0.5 micron or 1 micron here. And the approach we use here, basically the memory is that we only need the minimum number of the unique DNA sequence to form the template, and we also can change the repeated unit easily to form a longer template or a shorter template. So you see that basically we can use a modular approach to control the, each building block of the DNA with a better control of their dimension, length, geometry, and also the flexibility. So what would be the next things we would like to solve is whether we can take these as a tools to place the materials in a precise position along the tube length, and then at the end to release that gas molecule in response to external stimulus. And to do this, we just have to modify the design a little bit to generate this kind of nanotube with the longitudinal variation by alternating the large and then the small capsule here. And to study the encapsulation inside the nanotube, first of all, we assume that the gas molecule should not have the affinity to the DNA so that they do not stick to the DNA unless there is encapsulation. And to prove this idea or demonstrate the idea, we are taking a gold nanoparticle, which is 15 nanometer diameter, with citrate coated, so which is negatively charged on the surface, and our DNA is also negatively charged. So we assume that they should not come together unless there is encapsulation, which means that the gold molecule should only sit in the large capsule with a regular distance. And from the AFM and the TM study, we also confirmed the spacing and also the people architecture from this kind of nanotools. So after we encapsulate the materials inside, so how can we release them? So in here, we just try to modify a little bit on the design to have the the sticky end with the egg-based overhand DNA strand on two sides along the nanotube. And then we add the complementary eraser DNA strands. So what happened is that the closing strands are removed and form the double helix here. And at the end, the nanotube becomes partially single-stranded, and the capsule are open now. So the gold nanoparticles are completely released from the nanotube. And we also study the kinetics, and that process is very fast, just finished within 15 minutes. So you can see that we have demonstrated here that the DNA-based nanomaterials or nanostructures could be a good candidate for the purposes for drug delivery. So in the open state, we can put in the molecule, the cargo, and then close the tube, transport the tube to the target cell, and then selectively open the tube for the drug delivery applications. But you can see that here we are just adding the extra DNA strand for the purpose. But you can see other external molecular input have also been used to change the conformation of the nanostructure in here. For example, we can just, by changing the pH and also adding the small molecule to open up this kind of capsule, or even we can add some metal ion to change the morphology of this tetrahedron. But you can see that if for the biological purposes, basically this kind of approach will generate waste, okay? And this waste is quickly accumulate and which are non-biodegradable, and then finally will induce toxicity in the biological systems. So recently, Tang group also tried to, using another approach, using the light, to induce the molecular change inside this DNA nanocaesar. But we know that using the UV light basically can cause serious damage to the cell and also for less tissue penetrations. So our idea here is for the biological purposes or application, we would like to, using a 2-photon excitation as a nice source to, eliminate the stimulus, because this kind of approach can give an instant response time, and also this is a long wavelength excitation which will allow for the deep tissue penetration and less photo damage of tissue. And again, since no waste is accumulating in this approach, it is a clean switching mechanism. And more importantly, we can remotely control and optimize the entire process. So our idea here is try to modify the nanotube with a 2-photo labile molecule as shown here with red color, and design the tube with some hairpin, the single strand sticking out. So what happened is that once we excite with the 2-photon laser, basically the 2-photoreactive molecule should cleave, by themselves, and then expand the cavity along the nanotube and become a flexible nanotube now. So we're using similar approach to generate this linear nanotube with a long tubular structure from different characterization. And our preliminary result found that after the excitation, right now our nanotube become bending nanotube with some degree of curvature from the confocal and also the TM study. And opening or the expanding of the cavity is also confirmed by the fluorescent measurement, because in here we have designed the strand here with the dye and the quencher. Before excitation, they are close to each other, so that's why the fluorescence here is decreased. But after expanding the nanotube, the distance between the dye and the quencher, they are far away from each other now, so the fluorescence from the dye will be increased dramatically in here. So basically, right now, we believe that this approach will be a safe and clean method for the molecular switching for biological applications. But if we consider this kind of programmable DNA nanostructure as tools, for drug delivery in the biological system, first of all, we have to solve different problems and answer some questions first. For example, what is their cellular uptake mechanism, and where are they after they are taken up by the cell, and how stable they are, and also are they still interact, and will they be degraded before taking any biological applications. So in here, to have a better understanding of this kind of molecule in the biological system, we would like to first get rid of the endocytosis pathway to let them get into the cytoplasm directly before they are taking any reaction or behavior. So recently found that most of the cell-assembled DNA nanostructure, they will enter the cell through the intrinsic recognition properties or the non-specific uptake or just functionalization with the targeting group. And most of them, they are localized in the acidic environment, such as in the lysosome or endosome, and being as partially intact nanostructure. So this is not what we want. We want them to be stable and they can carry their function immediately. So here we would like to introduce a new method to deliver them to the cytoplasm directly. And what we're using here is try to using a silicon nanowire approach as a delivery platform. And this nanowire array, basically we functionalize that with some amine on top with positive charge. And then we put our negative charge DNA sample on top. And after that, we place the cell. And after 30 minutes, basically the cell can penetrate through the nanowire. And then our DNA sample can release directly to the cytoplasm for imaging. And at the same time, we have this delivery approach, and we also have to modify our DNA sample here, taking a DNA cage, with some organelle localization signaling peptides using the typical solid phase fragment condensation reaction. Once we have this DNA cage carrying 3 specific peptide sequence, the models, we just try to put them into the cell. And basically, we found that depending on the sequence we use to put on the DNA cages, the DNA cages can be successfully localized in different subcellular environments. For example, in the mitochondria or in the nucleus. So, one question you may ask, how we can apply this delivery approach for in vivo or further biomedical study? So the answer is yes, it's difficult to do that. So the further advancement in the development of the structure, we would like to modify one of the DNA strands here with a lipid molecule with the alkyl chain, the C18 chain models here. And then once again using the molecular approach to form these cages. And surprisingly, we found that these lipid functionalized DNA cages can be internalized by common different cell line with high efficiency, and all of them localized exclusively in the mitochondria without any using of the transfecting reagent or even the delivery platform. So we believe that this modification is good for us to further study of the biofunctional properties of the cages in the subcellular environment. And also from the FRESH study, we can see that our new modified lipid cages can be stabilized, being an intact structure in a cellular environment more than 72 hours. And they also exhibit a low toxicity in the cellular environment. And on the other hand, for the peptide functionalized DNA cages, they start to degrade gradually, after 24 hours incubation. So you can see that only a small chemical modification of the DNA strands, it can give you a dramatic change in their biostability. So to demonstrate this DNA nanocage or the structure can be used as a nanocarrier, we just take a V-carboxyl molecule as a cargo, which has been proved as a fluorescent-like probe and also a minor growth binder for duplex DNA. So from the gel analysis, we can see that this V-carboxyl, the molecule, the cargo, were successfully loaded onto the cages with a lower mobility on the gel as compared to the control one. And also they have the overlapping of the fluorescent from the cargo and the cage. And from here is the titration data of the V-carboxyl. And based on these data, we can estimate the dissociative constant of the cargo to the nanocage, which is found about 1.3 micromolar, and which is much smaller than the KD for the duplex DNA. So you can see that this would be proving that our DNA cages is a better carrier than a double-stranded DNA for this kind of cargo. So to prove that, we can use the cargo for the delivery, we studied the confocal colocalization experiment. We can see that in the presence of our DNA cage, the cargo molecule V carboxyl was successfully transported and delivered to the mitochondria, as compared to the control, they just only bind on the surface of the cell surface. So the ongoing work in my group is trying to develop a gene silencing DNA nanocarrier, and by integrating the antisense oligonucleotides as one of the construction elements, and later on for the further gene expression modulation. So to summarize my talk today, I hope I have shown you that DNA is one of the most useful engineering materials available in the nanotechnology, and it has the potential for the cell assembly and the formation of the programmable nanostructures. And by using different approach, we can modify these structures to make them more interactive with specific biomolecule or biological environment. And I have also shown you the examples that they could be one of the excellent candidates to develop the multifunctional target drug delivery systems. So thank you for attention. And I would like to special thanks for my students, because they just joined my group, less than 2 years, and they already did some wonderful work in here. Thank you for attention.
Well, thank you, Dr. Lu. That was an interesting introduction of a application in a different dimension, bioapplications. Now I'd like to introduce a colleague of mine in the Department of Physics and Material Science, Professor Rogac. He's a chair professor in our department and a founding director of the Center for Functional Photonics at CityU. Professor Rogac received his PhD in chemistry from the Belarusian State University in Minsk. And he worked as a staff scientist at the University of Hamburg from 1995 to 2002. And from 2002 to 2009, he had a tenure position at the Ludwig Maximilian University in Munich. His research focuses on synthesis, assembly, and optical spectroscopy of colloidal semiconductors and metal nanocrystals, quantum dots, and so on, and their hybrid structures, as well as their use for energy transfer, light harvesting, light emitting device, and bio-labeling. So you can see it's a range of applications. He has published over 260 papers and book chapters in these areas, which have been cited 17,000 times so far, with an H index of 70. He was named a top 100 material scientist by Thomson Reuters, and he also serves as an associate editor of ACS Nano. The title of his talk is Advanced Light Emitting Nanomaterials. Let's welcome Professor Rogac.
So I would like to thank Shun Li for inviting me here. We had a wonderful talk by Peggy given on DNAs, which are building blocks for nanostructures, as we just learned. And in my talk, I will... The title of my talk is Advanced Light Emitting Nanomaterials. And essentially these are colloidal nanoparticles. We have seen some examples of gold colloids in previous talk. I will mostly focus on semiconductor nanocrystals, which we also call quantum dots, as long as they're spherical in shape. And the second part of my talk is on carbon dots. And these materials are nice light emitters. And that is why they are good candidates for light-emitting devices, LEDs. And this is my example in my talk on their use in, let's say, real-world applications. So nanocrystals which we are working on look like shown here. These are crystalline particles. They are tiny, like 60 million times smaller than soccer ball, which is roughly the same distance as from the soccer ball to the S. And what is very nice about these tiny objects is that we can control their emission by changing size. This is called size quantization effect. If we make them smaller, they emit more energetic light, which means for this example of cadmium telluride that we can tune emission from 2 nanometers, from green to red if we change size. And this is something which chemists can do very well now by using chemical synthesis. So we always synthesize them in liquid phase. That's why you see here those examples like light-emitting flasks. And then we can process them in film structures, in devices, and so on and so on. In fact, we developed this slide at one point in Germany when we wanted to show some visitors for German parliament called Bundestag what is the difference between macrovolt and nanovolt. We wanted to tell them that in macrovolt, if you change size, nothing happens, or almost nothing in terms of properties of materials. And for nanovolt, we change size, very precise way, and we change their optical properties. One way to tune emission of colloidal semiconductor nanocrystals is by doping. And this can be done by ion exchange, which is schematically shown here. So we start from cadmium halcogenides, for example, and then we introduce mercury ions, we introduce different other cations, and by that we can tune emission of these nanocrystals alongside with the change of size, as I mentioned on my previous slide, and this is what we are aiming at. And nowadays, it is important to move the emission not only over the visible spectral range, which has been done for quite a number of years, but also to go to the near infrared. And mercury telluride here is an example of material which emits very strongly in the near IR. And then this can be used for, in particular, for biological application, because then you can see this emission through the skin of a mouse. And if we go back to the previous talk, this actually is a method which is quite often used to look how drugs are uptaken by living bodies. Those drug delivery systems are marked by near-infrared emitting nanocrystals, and then we can watch them how they go to a cancer place, for example. So, I cannot see it from here, okay. Very often when we go for emission in the visible spectral range, we use cadmium telluride nanocrystals. And this material for my group in particular has a very long history, so this was a very fast publication, which I made when I came as a young postdoc to Germany. And then you can see that regularly we come up with some other publications on this kind of material where we report some improvements of light emitting properties and some other factors. This is a good material for visible spectral range. Also it comes already to near IR. And emission characteristics are good. So what we call photoluminescence quantum yield is high, 40 to 80%. And we also learned from the previous talk, it is very important how Cephas is designed for nanostructures. We call these molecules ligands, and these ligands play a crucial role how we can bind, for example, these nanocrystals to DNAs, to some other biological entities, and so on and so on. So the ability to control the properties of the core, light-emitting core, and the chemistry at the surface is very crucial in this whole business of colloidal light-emitting nanoparticles. Starting from cadmium telluride, we can import some other useful functionalities to these quantum dots. For example, this from here, actually, I will give you mostly some recent examples from our work here at CityU. Most of the citations here, you will see they are from 2013, 2014. And here, we created something more complex. We call these particles core shell, because we start from cadmium telluride core, which gives us this emission in the near infrared, 650 nanometers. We coat them by a shell of zinc sulfide. By that we reduce toxicity of those nanocrystals. And then we also put some dopant into the shell, which is manganese. And manganese is magnetic resonance contrast agent, which means that we can follow those particles in a body, for example, both by near-infrared emission and by doing MRI measurements, which is very useful for a number of reasons. I mentioned that ligands on nanocrystals are important, and this is still an ongoing topic for research worldwide. Here you can see that we decided to employ this cage-like ligand, which is called polyhedral oligomeric silces-coxane, to synthesize cadmium selenide quantum dots in that case. Again, we tune the emission by size of the core. And into this particular cage, we can, for example, place some ions or some small molecules. The emission may be quenched or enhanced, depending on the interaction with light-emitting core, and this is a sensor then. Or we can process this kind of coated cadmium selenide nanocrystals in a very high quality thin films, because these are building blocks for silica gels. So here there will be a few examples on ion exchange, which I mentioned before, and this is one way how we may make cadmium mercury telluride nanocrystals. Again, we start from cadmium telluride, then we introduce mercury, and then mercury will substitute some cadmium ions from cadmium telluride, but there may be at least three different ways how it happens. There may be homogeneous alloy, there may be some concentration gradient, starting from the surface, which will be mercury rich, and the inner part may be still cadmium rich, or there may be something what we call core shell structure, well-defined two-phase system, cadmium telluride core and mercury telluride shell. And all this scenario may happen. We typically look on the fate of those particles using optical absorption and photoluminescence spectroscopy as the major tools. And for example, what we can see from this slide, you can see that the higher mercury ion concentration which we introduce indeed moves emission of those alloy nanocrystals towards longer wavelengths, and this is nice because by that we go into the near infrared region. Also this characteristical Stokes shift, the difference between absorption where we can excite them and the PL maximum changes, and this all gives us some hints how distribution of mercury occurs when we conduct such kind of reactions. We can also start from nanorod-like particles, in that case cadmium selenide rods, and if we do very similar reaction, mercury exchange, then we actually find out something interesting in terms of phase transformation of those nanorods. Cadmium selenide original rods are Wurtzite time, and it seems that they convert gradually into mercury selenide zinc blend nanoparticles. And by that, the emission in the near infrared appears as well. So from that point, I will switch my topic from quantum dots, from semiconductor quantum dots, to what we call emerging light emitters carbon dots. There is a lot of interest to these materials nowadays. They are much younger So quantum dots, actually this year they celebrated 30 years anniversary, which is the same as CityU, correct? And Mark is coming from University of Berkeley. One of the very well-known name in this field is Paul Elevizatos, correct? Who is your colleague in Berkeley and who is also the director of Lawrence Berkeley National Labs. So carbon dots are much younger. They were reported maybe 10 years ago, but one big difference to traditional quantum dots, which I introduced to you before, is that they are considered much less toxic. Recall I gave you example of like cadmium telluride, mercury telluride, all these metal cations, cadmium and mercury are toxic. And even so, in some cases, they can be used also for biolabeling, but apparently carbon dots are better for that. They are claimed to be good for drug delivery, tumor imaging, photoacoustic imaging, photosynthesizers. These are all areas related to biolabeling or bio applications. Our area is more here, light-emitting diodes, and we just got accepted very recently one review paper in Nano Today where we summarize all these application areas for carbon dots. For my group, we started to work on them 2 years ago, roughly, and I will show you 2 examples of how we can control the light emission properties in terms of tunability of light. So one is on thickness-dependent full color emission tunability in a flexible carbon dot ionogel. For us, it was very easy to go from or to transfer our expertise from quantum dots to carbon dots, because for us these are all colloidal nanocrystals, colloidal nanoparticles. They have light-emitting core, as I mentioned, and they have some surface chemistry. Surface chemistry is important here if we want to make composite materials out of them. So for making ionogels, we started from organosilane functionalized carbon dots, short name like here. For that, we use very environmentally friendly synthesis. Citric acid is a cheap organic molecule, and by high temperature pyrolysis in the presence of this silica-containing molecule, we get particles which are schematically shown here. They're tiny, like 1.2 nanometer diameter. They show all these characteristic peaks in FTR spectra, which tells us that they indeed look like here. They have graphite-like core and selenized surface. And optical properties of carbon dots, they are quite different, in fact, to the optical properties of quantum dots, semiconductor quantum dots, because their emission is not so much size dependent, but excitation wavelengths dependent. What you can see from this photograph and also from this collection of photoluminescence spectra. So we take one and the same sample, we excite them at different wavelengths, and you can see that they can emit green light, blue light, green light, also yellow light, one and the same sample. Their absorption spectra look like shown here. They show a number of what we call molecular-like transition, like pi star, NP pi star, and their emission, as I mentioned, it is tunable by excitation, by the wavelengths of excitation. They emit strongest in the blue range. Green emission is still rather strong, and if we would like to get emission shifted to the yellow part of the spectrum, to the red part of the spectrum, this emission is typically very weak. We would like to improve it, but blue emission is near perfect, so it's 80%, it's very perfect blue emitter, much better than, I would say, any blue emitting semiconductor quantum dot, which you may be able to find worldwide in the market or in some laboratories. So about the origin of photoluminescence here, there are still some discussions in literature. It may be related to sp2 domains or SPC3 type carbon defects which are closer to the surface, while these are domains in the core of carbon dots, so the investigations here are still ongoing. But the fact that we can control the emission by excitation wavelengths, we actually realize it and I will show you on my next slide how we did it. First of all, we produced composite materials, which we call carbon dot ionogels. So we mix solution of carbon dots with ionic liquid of some particular formula. We age them for a while, and then we get such large area actually. So the thickness here is 2 micron, and the size of the sample is like here shown, and we can make it even larger. These are flexible pieces of plastic essentially, where we embed carbon dots with a high concentration. So this color which you see here comes from the lower transparency of carbon dots or wavelength starting from 500 nanometers and longer. While for shorter wavelengths, this material is perfectly transparent for light, which means that we can excite it easily by UV light somewhere here. And then what we found out was that if we take a block of such ionogel and we excite it at different distances to the edge, so we collect light always at the edge here, but we can excite it close to the edge or at longer and longer and longer distances. And what we found out is that we can actually move or change emission of these ionogels, starting from the blue, if we excite it at the edge, going all the way through all other colors to the deep red color. And emission stays quite strong if we keep exciting them at short distances, and then it decreases gradually if we go far from the edge. So why it is like that? This is a direct consequence of 2 factors: high concentration of carbon dots in the ionogels, and the fact that the emission depends on the excitation wavelengths. Here, in fact, you can see real color images taken when we excite thicker blocks, or thinner blocks, sorry, then they emit blue light. If you go for thicker blocks, like 10 microns, they are definitely red. And every color in between is possible. So how it works? If we excite them thin film, then propagating light essentially excites some amount of carbon dots like it would be in a diluted solution. So there is very little reabsorption and re-emission for thin thickness, thin films. If you go for thicker films, then at some pathway, carbon dots will be excited. They will re-emit light at the wavelengths which is shifted to longer wavelengths. Then that emission will excite next portion of carbon dots, and because the emission is excitation dependent, the outcoming light become green. And if the pathway is becoming longer and longer, there will be a number of these reabsorption and excitation events, and by that we shift the emission to the red. And by that we can achieve the full color tuning depending on the thickness of these materials. So now let me go to real devices, to LEDs. One example about quantum dot-based devices, again cadmium telluride, and in that case what we did, we make them again in solution like we always produce our samples. We mixed them with sodium chloride, which is just a normal salt. If you go to a canteen, you get salty food. This is because of this sodium chloride salt. Yeah? And if we mix them together, we essentially very efficiently protect cadmium telluride from the environment by embedding them into such kind of powder like you can see here, where they are surrounded by salt. So we call them salty dots. And you can see that these powders emit any color of light which is possible to achieve with cadmium telluride quantum dots, from green to red. And then devices which we made here, they are cadmium telluride quantum dots embedded into sodium chloride, dispersed in a polymer matrix, and placed on top of a UV chip, which provides UV excitation. And then, depending on the color of emission of cadmium telluride here, we can get outcoming color. This is an optical way how to address LED. It's not an electric ejection of electron holes, but excitation by UV light. And you can see that this solid-state luminophores, they may change their color from green to red. Again, focusing more on carbon dots, we now design them in a way making them suitable for electroluminescence. So these are real light-emitting diodes, where we inject carriers, electrons, and holes by injection, by applying an external bias. So we made carbon dots soluble in organic solvents, in octadecene, using some other ligand, because in that way it is easier to process them into thin films. So these particles are slightly larger, 3.3 nanometer mean size, still nice blue emitters, like you can see here. Solution photoluminescence quantum yield very reasonable, 40%. And then this work has been done actually mostly by my postdoc here, but he is at the same time associate professor in the University of Jilin. And they have all the facilities to fabricate LEDs over there. So in my laboratory here we do material fabrication, we do a lot of optical spectroscopy, but we don't make devices. So Zhang Yu, my postdoc, he prepared devices in Jilin University, Changchun, and what you can see here are examples of different colors of carbon dot-based LEDs. So this is a structure of LEDs. There is a hole injection layer, electron injection layer, a light emitting layer in between, which is based on carbon dots. The so-called 10-on voltage of these devices, that's the voltage which we apply and they start to emit visible light, is 6 volt. And we have seen that the color here is very much depends very much on the current density, on the amount of current we can inject into these devices, which is probably even better seen from here. So if we apply lower voltage, like 6 volt, those devices emit mostly blue light, and if we increase voltage, it moves to cyan, magenta, and white. White is like that. That's also related to the spectral profile of carbon dots. You can see here it is quite broad, and if we inject current at low injection density, then the blue emission, this channel here, prevails. We have done some studies where we compare electroluminescence with photoluminescence, and again I recall you that photoluminescence of carbon dots can be movable over a broad spectral range depending on the excitation. So what happens here is that if we increase current density, then we address higher energy states in carbon dots. Those higher energy states can feed the lower energy states, and by that we add colors of other, emission of other colors, like 460 nanometers, which is here, or even longer wavelengths, 580 nanometers, if we increase current density. And by that we change the neat emission color of those devices from originally blue to up to the white color. If we combine orange and blue, we end up with white. And we were sure that it works like that because when we made some other configurations of devices, for example, here we increased the thickness of this electrode over which we inject electrons, and this leads to lower injection current density. So for that device, we could only get blue color. If we, on the other hand, improve injection current density by using this additional zinc oxide layer, which is a very good electron conductor, then we achieve devices which emit only white light. So we can control emission color here on purpose by varying parameters of these devices. And coming back again to quantum dots, I mentioned that people dislike them very often because of toxicity of cadmium, which is often a constituting element. But there are other kinds of quantum dots, like zinc, copper, indium sulfide. There is no cadmium here, and those kind of nanocrystals, they are now very much in focus as cadmium-free alternative to traditional quantum dots. And here we used a very simple, straightforward RGB concept, which is red, green, blue color. So combination of red, green, blue color placed together on a single device would give us white color as a result. And this is one useful way how to make white light-emitting diodes. So we combine blue color from carbon dots and green and red color from quantum dots of this particular composition, mix them together in different proportions, again excite them optically by UV light, and then we can get white color with different shades, like yellow shade, bluish shade. For this kind of big room, for example, we would like to have white color with yellow shade. We feel ourselves better in such rooms rather than with pure white color, bluish white color illumination. And this is all possible by making such kind of devices. So to conclude my presentation, I started from colloidal semiconductor nanocrystals, quantum dots, and I mentioned that they are meanwhile 30 years old. So Shun-Li mentioned when he introduced me that I am also an editor of ACS Nano, so we have to come up sometimes with what we call editorials, and this is a very recent editorial from myself where I remind the community that quantum dots still shining strong 30 years on. So there is a lot of activity still in this area. And these semiconductor nanocrystal quantum dots, in some areas, they are developed to perfection as light-emitting materials, in particular also for LEDs, in fact. So they have been used in some very recent modifications of large-screen Sony TVs. But there are some concerns about them, like toxicity of cadmium. And in recent years, carbon dots have emerged as yet another very attractive light-emitting nanosystem. The mechanism of emission here is different. Here, size and composition dependence. Here, excitation, tunable emission. But again, very tunable, very rich surface chemistry, so that in both cases we can handle these materials like chemicals and make some functional structures on demand. And both quantum dots and carbon dots are heavily researched nowadays as components of high color purity LEDs and white light emitting devices. So you can see here names of the members of my group, and many of these people are gone. And this is actually nice at the university. Yeah? So people finish their PhD, they are gone, we get new PhDs, and this is ongoing process. So this is essentially, I have been here for 5 years. Mostly these are my first generation PhD students. Some postdocs are still around. And I would like to thank also funding from different sources in Hong Kong and also UK. And I thank you very much for your attention.
Thank you, Professor Rokac. Actually, it's incredible. We're on time. This doesn't happen very often. At last, I'd like to introduce our last speaker, another colleague of mine, Dr. Roy Vadasamy. Dr. Vadasamy is an associate professor in the Department of Physics and Material Science, and his research is truly interdisciplinary in nature, which is a blend of physics, chemistry, and material science and engineering. He is leading a group of physicists, chemists, engineers for the fabrication of functional self-assembly materials to devices and integration of such devices for printed electronics and energy harvesting applications. He was awarded the TRIO Fellowship in 2003 by UNESCO and Excellent Product Awards for project, prototypes, at China's high-tech fair in 2012 and 2013. He has published more than 80 papers in international journals, including Nature Communication, Advanced Materials, Nanoletters, and so on. He and his co-workers had filed 5 U.S. as well as international patents on the devices that the group has manufactured. For those of you who don't know, Roy is also a devoted martial art practitioner. So in the field of martial art, he is actually the descendant of Yip Man, who invented this Wing Chun. And he's teaching a gateway education course on physics of martial arts. So without further ado, let's welcome Dr. Roy Velasamy.
So good evening, everyone, and thanks for Professor Wang Shunli for his kind introduction and the invitation. So I'm going to talk something fancy stuff. I'm holding in my hand some of the sensors that we made. We call it electronic skin that you can wear as a flexible device. Okay, thank you. Okay. So, without delay, this is my topic, functional material for plastic, memory and sensors. So why we call plastic? Because we built up everything on plastic sheets, like PET, polyimide, different kind of polymer layers. Now, flash memory, I start with the flash memory. It's a very wonderful technology that we are all using today. It's a tiny piece of USB drive. You can copy and carry wherever you like. It exactly work like our memory. So even if you don't have voltage, it carries the data. And then you insert it on your computer, then you apply BIOS, then you can write, erase, whatever you would want, you can do, you play around with that. So now, all this technology that you have in your hand, like mobile phones, computers, or camera, everything have inbuilt memory device. So this is a CMOS-based technology that we are all using it nowadays. So this CMOS-based technology is grow quite fast, and nowadays we have just 10 GB memory. You can just go to the market and buy for a couple of bucks. So cheap and stays longer. So as I show you introduction here, it has multiple, all these devices that we have, all have memory, flash memory device. Now this is one of the examples. Now it also have a lot of money in this area. So it's multi-billion-dollar industry that all these gadgets that we use have these memory devices. Now I'm going to show you a different kind of memory device that we are not, some part of the world is really using it. Like if you go to Germany, the train ticket, the metro ticket, these are all memory, is a plastic memory, a piece of polymer paper that they can write and read multiple times. Now the conventional electronics, that USB drive that we have, usually have for high data storage. But can we transform these devices on a piece of plastic? Okay, so in that case, it's always kind of compromise. You don't expect that 10 GB or 100 GB memory in a piece of plastic, but you expect some other functionalities that those conventional devices can't do that. So here what we have is have a large area and completely flexible and simple fabrication technique that you can use printing, like gravure printing or screen printing, all this printing technique to print. So these are the main advantages. Okay, so I'm going to talk about this printer electronics part today. Now, it all starts with a very simple transistor structure, and it's very easy to understand. What you have in your hand is a water tube, and one is a source, another one is drying. When you pump the water through the tube, and you use a third terminal to control the flow. Okay, this is how your CMOS technology works, that your mobile phones, all this stuff. So this is one of the very beautiful review by one of my collaborators in France, for which he explained how it works. Now, in fact, I did a lot of work on the semiconductor part. Okay, I've been working on for the last, since 2005, almost 9 years. We published a lot of papers on organic semiconductors, how to deposit. This is one of the oscillator, a ring oscillator that works with some hundreds of kilohertz frequency that we made. In fact, when you make a semiconductor, you're putting on a dielectric layer, and the semiconductor can be a molecular material, but you put it on an oxide, you always have an interface problem. So this interface is full of traps. How we are going to overcome the traps, that's one of the important things. So these traps always behave like an obstacle for the charge when they're transported, as we see in the previous slide. So when the charge flow on the semiconductor, on the first couple of or 3-4 monolayers, these traps just behave like an obstacle for them to flow. Basically, they trap these charges at the oxide interface. Now, these are one of the main reasons that why these devices do not have a high mobility. Okay, so can we use this for other purposes? So that's what we did. We can use these traps to store the charges. So whenever you want to release the charges, you apply negative bias, you release them off. So it's basically like you program, erase. So this is where the memory device is born. Now, after doing a lot of work on semiconductor devices, then we, after I joined CityU University, we start to work on interface. Okay, how to fill the interface, then or you artificially create more traps, okay, to have more charge trapping elements at the interface. So this was the first work. We start, for the last 4 years, we have been actively working on this area. So we embedded nanoparticles, either gold or silver, here is gold, in a polymer matrix. Okay, this is an interface, and interface with the deposition of the organic layer on the top, it looks like different morphology, depends on the size. So what is the optimum size? We fix with around 10 nanometer, because if larger the size, in fact, it can store larger data or basically larger charges, but then if the size grows longer, you have other problem like intruding the next layer, adjacent layers. So we fix with 10 nanometer, where you can program and erase multiple times without any trouble. And these devices, so all these flash memory devices basically have two problems. One is the memory window, how big the data can be stored or how large. Number two, how long the data can be retained in a particular device. So retention time and the window, we call memory window, which is the data storing capacity. These are the basic problem. Our conventional silicon-based devices, you store the data and leave it for a couple of years without touching it, you start slowly losing the charges. Okay, so because the retention time is much smaller. So and we work on both areas, we explain one by one. So we start to think about how to trap both electrons and holes to have a larger memory window. First of all, we try to solve the problem of memory window, have more density. So we design a structure with the two molecular materials, which is both can be solution processed, and with the gold as electrode. You can see it works in both electron and hole enhancement mode. So basically you can trap both electron and hole in the device. And they form a beautiful crystalline structure on the surface, okay? And you can program in electron and hole enhancement mode. Basically you can program electrons or you can program holes. So it works in both the mode. Now, all these devices, what I'm talking about, is have a single layer, okay? Now, in the device structure, if you see, you are storing all this data next to the dielectric layer, which is called floating gate. Now, if you don't have a layer, all these charges come from the semiconductor layer can get back to the semiconductor layer. So we put another layer called tunneling dielectric layer, which is just 10 nanometer. So by doing so, the charges cannot easily get back. And you can enhance retention time. That is how long you can store the data inside the device. Now, as a first part, we start to print, contact printing method by using a metal nanoparticle, which is gold here, and using a simple PDMS stamp and transfer from one substrate to another substrate. And since they have a charge, they don't form multi-layers, and they just form a beautiful one monolayer. So we embed this layer between two aluminum oxide insulator. So when the charges are getting from the pentasene, the semiconductor, to the gold nanoparticles, now these two aluminum oxide layers, they confine the charges in a particular monolayer. So the charges stay much longer time than the previous devices. Now, then we try to understand how these nanoparticles, in comparison with a film, okay, or use a substrate, dip into the solution, and self-assemble the nanoparticles. So just try to compare. Now, what's the beauty of these devices? Each particles can hold charges. Now, our conventional devices, they all form as a film. So when you have a film, when the charges are trapped inside the film, they can always leak laterally. Okay, so there are two kinds of leakage. One is a lateral leakage, and another one is a vertical leakage. But if we have a defined layer of particles on the particular monolayer, these charges are confined in each and every nanoparticles. So basically you don't lose them. So this is the reason, the beauty of this nano floating gate. Now, you can see here, comparison is a contact printing method, and the self-assembly method, and the evaporator means just a film. In fact, we have larger memory window because more particles means you trap more charges. And what about the evaporator is somewhat similar, but the retention time of this layer is much poor. Because it's just a film, the charges can always leak laterally. Now, this is a video that shows mouse. What is that?
Play the movie?
Yeah.
Maybe this is a different version.
Okay, just leave it, okay. So I just want to play a movie, but so we try to apply stress and strain at different angle and try to understand how the bending test mechanics, because there are plastic substrates, we have to understand the mechanical properties. And this, you can see that at multiple programming states with a particular bending radius, okay, it works perfectly well. And also it can be programmed and erased with a multiple program erasing cycle. Now, okay, still there's a problem. Why? If you see the structure of these devices, the nanoparticles, the work function matches well with the homo level of the molecule that we use. So even though you have a tunneling oxide, the charges can still get back. Okay. So what you are going to do is, there come the graphene oxide, or reduced graphene oxide, which is basically graphene. We artificially create another barrier so that the charges cannot easily get back. So we put a layer of reduced graphene oxide, so stop these charges to get back. So you have a double barrier, and the retention time enhanced twice. So this is the way how we make the device. We pick up a just PET substrate and functionalize with the nanoparticles with a negatively charged, and then we have another polymer which is positively charged, which is PAN, and fill up the graphene. So these are all layer by layer by charges. So these charges attract each other and stick together as a whole device. And finally, we have a tunneling aluminum oxide, and the semiconductor as a whole, the device looks like what you see here. And we used the saturated density of nanoparticles so that the memory data storage must be much higher. And you can see the difference. One is without the graphene oxide, that's graphene, and with and without graphene. So here you have a graphene, you can see twice the memory window. So what is happening here is the nanoparticles, of course, they trap their own charges, and in fact graphene is a kind of a strange metal that we know also start to trap charges. So you have two kind of trapping layer. Plus, this graphene has a kind of smoothing effect, not allowing this particle to intrude into the semiconductor so they completely fill up the surface. So both together work perfectly as a trapping center and also give a barrier for the charges not to leak back. So twice the retention time and twice the memory window enhanced. Now, instead of making this layer by layer, can we make devices just put together in one layer? So what we did is, we take a reduced graphene oxide and dope with different metal chloride. So with gold, we've moved the work function up to 0.5 EV. In fact, you can do with platinum, palladium different, and we found that recently you can go up to 1 EV shift into the work function of the whole layer. First, we put the gold chloride, and because of negative Gibbs functioning, so they have a kind of redox reaction where the charges, they stick to the surface and release the chloride ions. And at the end, we put the semiconductor on the top and the electrodes. So at the end, the array of memory, it looks like the piece of plastic. So it works in both the N-type and P-type mode, mean both trapping and electrons. And you can see the memory window can go up to 2.4 voltage, which is much higher than the previous devices. And also we did one layer of nanocomposite, just embedding those nanoparticles, okay? And to have a simple device, just only one layer of charge trapping layer, as well as an interface between the blocking layer and the semiconductor. So it's a low voltage device because it's a polymer, and you can have 1 voltage memory window, but it's much smaller than the previous multi-stack devices. At the end, if you compare all these devices, in fact, in the layer by layer have a longer retention time. Like you have a layer of metal nanoparticles and the graphene on the top, because they have a two barrier where the charge cannot easily escape. On the other hand, if you see the compare the memory window or the data storage capability, the doped graphene is much better. You can go up to 2.7 voltage, which is much higher than these other devices. But if you see here, the retention time is much smaller. Why? Because you have a graphene on the top, you have a metal layer. This metal form like clusters. So at the end, it almost looks like a film where you have a lateral leakage. So because of that leakage, the retention time is a bit going down in compared with the layer by layer device. Now, in addition, we also did some molecular semiconducting device where you just simply spin coat a layer of carbon-60, which is a molecular semiconductor, but it can form like a trapping site to trap those charges. And it can work in both N-type and P-type mode. And in addition, we also put a polymer layer which has both electron hole transporting capability. It's a kind of balanced transport. So why we need a balanced transport layer? The reason is, okay, I trap electrons, then I have 1 voltage memory window. If I can trap holes as well, 1 plus 1 is a calculation, so twice the memory window. So with doing a balanced semiconducting layer, this metal nanoparticle has the capability to charge both, to trap both electrons and holes. So if you see these devices, it works in ambipolar mode in both trapping holes and electrons. So once you have a larger memory window, you can have multiple data storage. So as you see here, we can have up to 4 levels, level 1, 2, 3, 4 level of data storage. So for example, I have a device. This device can have a 100 kilobyte memory. If I can have 5 data sets, then just multiply with 5, so 500 kilobytes. So I can have a larger memory window, or larger data storing capability in comparing with just 1 data set level. Okay, this is the, after doing all kind of voltage-driven devices, we start to think, what would we do something with the light-driven devices? Fortunately, we have a pioneer in the department, Dr. Wang Feng. He do a lot of upconversion nanoparticles. So we talk to him and see how to use this infrared light to excite those upconversion nanocrystals where the light is absorbed by the polymer. So we basically it's a composite device where you use an infrared laser to excite those nanoparticles. And the emission is in the green region, as you see that, which perfectly overlap with the polymer. So the polymer basically reabsorb those emission from the nanocrystals. So it creates more exciton. So at the end, you apply a voltage to have more charges that you can play around. Means basically the light give you more charges. Now, we also did some of the work that I have tried to present with quantum dots. So what is the advantage of these devices? So when we submit the paper, we thought, okay, you have a device, a USB device, you can always set a password to open it, okay? But can we do a light-driven device? So basically, you have a precise wavelength of light that you can manipulate the data inside, something like that. Now, it looks fancy. Then we submit the paper, and the reviewer came back and said, oh, look, it has another application, something like that. What is that? He said, this has a lot of defense applications, so how it works. Then he explained in his reviewer comment saying that, okay, I have an infrared device, then you have for long-range communication, you have memory device that you can use just infrared to manipulate the multi-level data set it means basically for communication purposes. So, okay, thank you very much. Then we did revision all this more, and we make sure that this everything, because the problem is the mechanism, try to understand. So one is giving a light and we try to observe. So there are a lot of questions, are there any energy transfer on the excited state? Okay, so we need to solve. So we did a lot of spectroscopy measurements to understand, to make sure it's just a reabsorption of the light. So this is the AFM micrograph that shows different concentration of nanocrystals inside. So these nanocrystals not only emitting a light, but also it behaves like a charge trapping element inside the polymer. So when it emits the light, the polymer reabsorb and create exciton, which is electron-hole pair, and because of the energy barrier you quench, and this particle is again going to trap those charges. So then when you want to release them, use a light to release it. So basically use a light to manipulate whatever you want. And since the memory window is quite large, we end up with multi-level data storage. You can store up to 2 levels, and with light you can go up to, again, 1 more level of data. This is an ultra-flexible device. We just successfully made this with just 10 micrometer thick. So you can just cut like a paper. So and the retention time is not bad, it's good, 6. This is just a proof of concept. Okay, now I go to the second part of my talk. So we use the same CMOS technique to sense different kind of gases and toxic biogenic amines and drugs and so on. So all these things we do gas phase sensing. So you have, again, at the interface, you have different molecules. Because of donor accepting, we have different donors and acceptors, depends on what kind of molecule you want to detect. You want to detect the gas or drugs or so on, or biogenic amines, all in vapor phase, though you functionalize the substrate and understand the current change in the device. So these all, some of the device that I'm going to show is all, we use inkjet printing or simple solution cast. Now, this is one of the structure one of my coworker, Dr. Wu, worked with me to understand amine sensing. So basically, you have a color change. I can't exactly tell you what's the receptor and the acceptor we have because we are still waiting for the patent to pen, and some of them are, we already licensed this technology to one company, so I can't really tell you the structure of the molecule, but mechanism is basically you work donor acceptor. So when you have a charges, you donate to the sensor array, it not only change the color, but also give a current, because you have a semiconductor at the bottom that change the current that you detect. This I look like to play this, but yes, I can. So this is a small video that shows how we detect the drugs. It doesn't play. So one of the big problem in Hong Kong is detecting ketamine. In the US, you have cocaine, heroin, all these toolkits available to check in the spot. Yeah, it's fine, yeah. You can open. So, I can open up there, is it? So, in this box, what you see inside here is a ketamine, okay? It's a ketamine-like molecule. And then if you have a saturated vapor pressure, so we calculate something like 200 ppb of, and we dilute and put in this box, okay? And we try to measure how our sensor is working. So our sensor is basically here. It's just on a PCB standard printed circuit board, okay? Now, once you put it inside, and then we dilute by taking a syringe, the vapor pressure of the ketamine from here to there, and see the change in the current, what you see here. So why we start to work on ketamine? Because there's no toolkit available only to check, because ketamine is only popular in Hong Kong. So if you go to US, they use different kind of drugs. There's no electronic nose available to verify ketamine. There are some toolkits, but you need to ask, if you suspect someone, you need to ask him to give some body fluid to check. But this is just like a sniffer dog. So you just take like how people check the alcohol, you verify with the vapor indication from the vapor identification of molecules, different molecules. So what he's doing is taking the standard saturated vapor pressure from the big box to transform the small one, and you can see the real change of the conductance. So we calculate with the saturated vapor pressure something like 10 ppb, 10 spots per billion. So a sniffer dog can go up to 100 ppb. So what's the advantage? So how we are going to overtake a sniffer dog? Okay, so there are always people believe the biological sensing is much better than the electronic sensing. So only materials can make it possible. So this technique, if you have different kind of don't-acceptor molecules, basically you can detect food, drugs, explosive, volatile organic compounds. Everything is interaction between two molecules. And this is a simple comparison. So if you have a dog, usually it's more expensive. Why? You need to train, and you need to have people to employ to take care of them, feeding and so on. So we calculate our sensor this is one of the sensor head that we use. This is everything on a piece of plastic, okay? And the idea is you have a detecting nose where you plug in, play, just use it and throw it away. So this is the kind of comparison that we are working on. And so altogether, finally to give a conclusion, I start with the charge trapping properties of semiconductors, okay, and how to fill the interface to overcome the use of transistor-based structure as a memory. And then we have multiple different structures, layer by layer structure, to understand how these metallic particles, including functionalization of two-dimensional materials that can be used for charging the traps, and direct functionalization, as well as we discussed with the ambipolar polymer and how to enhance the memory window overall. And finally, we discussed about TFT structures as a sensing element for all vapor detection. And this is my group, and this is the electronic skin that we have in our laboratory. It's made up of PDMS, polysilicon, that mainly we make it for amines detection, okay. And then please don't count it. And then we have other kind of substrates. This is a memory array. It's on PET, polyethylene terephthalate. Okay. So these are all made in our laboratory. And we also have some industry collaborators to commercialize, because all my money comes from the Innovation Technology Commission, so we're supposed to commercialize those products. So thank you very much for your attention, and enjoy your evening.